Okay, so today we're joined by Samrat. He actually was my former RA in college, and he works for the AWS Outpost team. And he's agreed to do a mock interview with us. So very excited to have him.
Glad to be here.
So Sam, if you're ready to hop into the problem, we'll hop right in and begin.
Okay, let's do it.
Okay, great. All right, so in this problem, we're going to be dealing with multiple inputs. We're going to be getting a folders array.
Okay.
We're going to be getting an access list, and then we're going to be asked to determine whether we have access to a certain folder. Let's imagine we're just looking through a file tree, and we want to know whether a user has access to a specific folder. And so here we can see, okay, this folder 1, I'm going to query whether I have access to this A. Okay. And so I drew out like an example of this file tree. And so we're going to get this tree of folders. We're going to also get an access list. And so essentially if you have access to a specific folder, you have access to the folder as well as every folder below it. And so let's imagine I gave you access to folder A here. You would have access to folder B, you'd have access to folder C, and so on. And so that's kind of like the structure of this problem.
Okay.
And so the question is, okay, you're given these folders, you're given an access list, and then you're given a folder here. And then the question is, if we go down here, you're going to want to see, do we have access as a user to, a specific folder within the file system? And so I have two examples here. We have a smaller example of this ABC, and then we have a larger example of this ABF, GH, and so on. Okay. And then in this example, we say, do I have access to this folder G?
Okay.
And since the access set, we have an access set here, gives us access to this folder B, it unlocks all of these folders below it. And so we would return true because this folder is unlocked because it's underneath that kind of subtree. And so the question is, given folders, given the access set, and given the folder that we want to determine whether we have access to it, what is like the best way we can go about this in order to, solve this as quickly as possible and so on. And so if you have any questions, any things you want to clarify with me, you're free to ask any questions, and we can go from there.
I see. Okay.
If you're enjoying this video, we have plenty more awesome data structure algorithm and system design explanations on interviewpen.com. You can ask us any questions you have about any kind of topics surrounding data structures and algorithms and system design. We release 2 to 4 videos a week. You can run your code. You can talk to a personalized AI teaching assistant. And yeah, the site's pretty great. Anyway, enjoy the video.
Okay, so I guess you already answered the question in the beginning is so the permissions apply recursively. So it's like B, F, G, H, I, J, you would get access all the way through as long as you had access to B. Yeah.
Yes. If you have access to a folder, it's going to unlock that folder as well as everything below it.
I see. And are they all like folders? Are they guaranteed to have children, or can they be empty?
So we could have a folder that has no children, and we can also have a folder that does have children.
Okay. I see. So, okay. I'm just trying to boil down the problem space into what's relevant for us. Okay. So the folder structure, that's another thing. I guess you were adding like a array list of strings to the folders.
Yeah.
How do they map? Like, is it like
great question?
No? Okay.
And so essentially on the left, you're going to have the node we're dealing with, and on the right, you're going to have the parent of that specific folder.
I see.
And so this is essentially a list. This is the format of the input you would get. And so for example, A is the root of this folder system, this file system, or let's just say folders. And so it's going to point to nothing. Yeah, perfect. So we would label that the parent. We can see that who are the two folders that point up to A? Well, it's B and C. So B's parent is A, C's parent is A. And so essentially, this is a mapping a folder to its parent. And so that's the format of the input you're given.
I see. Okay. So I think the structure naturally leads itself into like, I guess you could think of it like a tree, right? With like children and stuff like that. Okay. So let me write down a few things here.
Sure.
How deep could this tree get? Is there any requirements?
Yeah. So this is a good question. Let's imagine that you don't need to worry about overflow within your program. You don't need to worry about Stack Overflow if you were to do this recursively. And let's imagine there's like, a couple thousand folders deep, but nothing where, within the constraints of wherever your program's running, you need to worry about that. We're kind of focused on the core of like, how do you think about solving this efficiently?
Got it. Okay. So I like to list out like all the requirements of what we're trying to achieve, which is like, the only thing we want to answer is like yes or no, right? Like given a folder and an access list,
right?
User has permission or not? True or false? That's it, right?
Yes. We only want to return true or false. If we thought of this as like a real world file system, maybe we like keep additional data, maybe, we do other stuff. But in this case, it's a very primitive, like, do we have access or not? Yeah. True or false?
Okay. I guess in a real world system, you would think about like whether like the access list can grow, and whether you have like cache it, and whether you have like be cognizant of like reuse of this function.
Right.
But okay,
Right.
let's just approach it from a basic angle first. Like there's a bunch of folders essentially like with children and stuff. As long as you have access to a top level folder, you have access to all the other children
Everything
folder.
below, yes.
Okay, so you could kind of boil down the answer to, as long as you knew every folder's parent, you don't need to check all the way down, right? As long as you were like kind of looking through as you're traversing it, as long as parent has access, you have access.
Yes, that's a good point. Yes, if you're sitting at a child node, if your parent does have access, then yes, the user would have access to you as well, since your parent is pointing down to you and that unlock would have occurred. Yeah.
Okay, cool. So let's imagine somehow you could construct this list of like A has children like B, C, D, E, whatever, right? Like let's say like A could map somehow you were able to get this answer.
Right.
And you knew that B was in the access set, or A was in the access set. Anything in these values has access to A. So technically, if you could somehow create this list, it'd be pretty easy for you to query your permissions.
Yeah.
Okay. So that's one thing I'm thinking of. Okay. So let's
yeah, I really like there's many ways you could there's many angles you could see it from.
Yeah.
And that is one angle where like, okay, we take the access we have, we take the like raw whatever structure of the files, and then we can say, here's this access list we can like query, and we just pre-compile down as like you're kind of leading to an access list we can just know immediately for a folder. So that makes sense. Yeah, I would just continue on the path and just continue to ideate.
Okay, so let's think about some like edge case scenarios, right? Like, could it be the case that you have access to nothing? If you have access to nothing, probably you don't want to check at all anywhere.
That's correct. That is a possibility.
Okay. Possible to have no access at all. Don't look anywhere because answer is always false. Okay. So true or false, it could never be the case. Could you have something in the access list that is not in the tree?
Could we have something in the access list that is not in the tree? Theoretically, yes, we could imagine that could be the case. It won't be the case with inputs you would get for this specifically, but let's imagine in the real world, yes, theoretically, we could have access for a folder. Maybe the folder gets deleted and we don't update the access list, and the access list points to something that's not there. That's potentially possible, yeah.
Okay, cool. That's okay. Yeah, I suppose it's fine, right? Like the access list could just have a bunch of random folders that you never have access to.
Right.
Or that's not in the folder list, and that's fine. Okay,
right.
So, all right. Okay, I think I've thought of most of the edge cases that I would be concerned about. Empty folders, we've said, like, it doesn't matter that it's an empty folder. No children is fine.
Right.
What else? Access list is fine. And these are all like strings.
Yeah. So yeah, strings for the title of the folder, and they're always going to be uppercase single letters, nothing malformed.
Okay. So that's something I like to clarify, is whether we have to do any kind of validation anywhere.
Right.
Validation not required is what I'm going with. Okay.
Yeah, everything will be well formed to like what you see.
Is constrained, won't overflow. Okay. So now that we know that like we essentially are limited by like how deep these trees could go of the folders, we know we have access to everything. I think largely now let me try to think of like some scenarios here. Is like what you could do every time is like, because as long as you can model this list of folders as like children, so like let's imagine you have like A points to like how do I represent children this way? Let me go this way. A has children, C and like B or whatever.
Yeah.
Right. And oops. So you could get into this situation where you're like a child has like C and B.
I just brought this down if you want to use it. Or
oh, cool.
Or I could delete it. Yeah.
Yeah, that's fine. And then B has like further children, right?
Yeah.
Or C, let's say C has a further children.
Right.
Like that, and then like F and G, let's say. Right. If you could somehow form this tree and you wanted to answer like whether folder G, whether the user has access to folder G, as long as the user had access to folder, like I'm going to mark with the access list, and this is like the question we're trying to answer.
Yes.
Okay. So if you were traversing down and you essentially wanted to find G, let's imagine this was just like a plain graph and it was like, find me G in this tree. If you hit like a parent, as long as you could keep propagating that information down, that like your parent, if you were on a node and you're going to traverse its children, you could pass down the information that, okay, at this point the user has access. So if you are a child under this parent, you're good. You'll always have access. So if you did just like if you could model this as a graph and then do like a depth first traversal, if we're imagining you go down like A, okay, A will be like, you don't have access to me yet.
Right.
And it'll pass that information down to C and B. And then C and B, when they recurse, let's say C recurses, it says, okay, the user does have access to me. I'm going to pass that information down to my children.
Yeah.
And once you hit the node you're looking for, you could just look at that variable that was passed in by your parent.
Yes.
And essentially just say you have access to yourself.
Yeah. So I like you're on a good path of
Okay.
thinking. There are two angles we could see it from.
Sure.
We could see it from like a top level propagation of, okay, this has access. Let's propagate that data down and maybe we cache this in a structure or something. And then you also started off your explanation of this as thinking bottom up in terms of
exactly.
what if we start from where we're querying, go up and say, when do we hit an access point? That is what's of interest to us. So, okay, I see you're coming from the bottom. I see you're thinking about coming from the top.
Right.
And we don't need to worry about, this is another thing I would bring up is like, will we have continuous queries? Because the top-down thing you said is interesting in the respect of, if there were 1,000 queries to this tree a second or something, whatever, let's imagine we have a server hosted and, we're repeatedly checking access. Maybe it might be interesting to have some caching. We won't need to worry about that for this specific use case where we need to maybe at intermediate nodes have information of what's above them. But
yeah, I guess it's good to think about, you make a good point that it is good to think about it from like both angles. Like, what is more efficient here? This is a thread I can pull on. Would you like me to explore like another thread of like how we could possibly approach this? So okay, let's actually clarify. Like there could be no like circular nodes, right? Like this is not a thing like where A is a child of C is a child of A.
Yeah, that's a good question. Yes, this will have no cycles. Cycles will not be an issue.
Okay.
This will be completely acyclic. Yeah.
Okay. Because one other thing you could do is now I'm just ideating at this point. Would you prefer I start writing code for this implementation?
I think we're at a point where we can like hop into like how we would go about this.
Sure.
And your approach looks good to me.
Okay. I'll write like step 1 is like decompose into a graph, and then step 2 will be like let's do a DFS essentially, passing data down to children. Would you like me to like create the graph out of the data that we've been given?
Yeah, you can represent this however you want to solve this as efficiently as possible.
Okay.
Whether you want to create your own class and so on.
Okay. So in the interest of time, I think the more interesting aspect is how the DFS actually works.
Right.
So I'll write the implementation of the graph later.
Right.
So I'll create like a fake class here, public final class, graph, and then fill in implementation. Okay, so let's assume we had this graph and you were able to fill it in with these folders. Right. Okay, so somehow you could create this graph and then you could run like graph.dfs, let's say, right, on a particular folder node. Okay, so now I'm trying to come up with the API such that we can like write a class that makes sense.
Right. And are you going to proceed with the solution starting from the top or starting from the queried folder? Which it seems like you're going to do top down.
Top down.
Either works. Either works.
Yeah. I think top down probably makes the most sense.
Sure.
And as I look through it, if I find like an optimization,
sure.
I can come back with it.
Sure.
So does that sound good?
Yes, that sounds good. As whatever we can do to solve the input output we are trying to achieve.
Perfect. Okay. So that has access, let's say. Given a list of folders, let's assume we have like created a graph. So okay, within this graph, let's call it like you can have like a node class. Okay, so what do we actually need? In my original idea, I said as long as you're traversing at any given node, what information do you have access to? My ID, I suppose, right? Like who I am as a folder. And at any given node, I can pass down information about like user has access here. It could be a Boolean, right? So if you could mark a node as like I have access and keep passing that information down, you'd be okay. Okay, so let's go with that for now. String ID or folder name. Let's call it folder name just to stay consistent. Boolean has access. And then, so let's just drop this to make it protected. Then node, you can give it like string folder. I'd forgotten how verbose Java is. Has access, and then you do like this folder name equals folder name. It's regular Java boilerplate. has access. Okay. So let's imagine we're like constructing the graph here. I'll do that at the end if I have time. And then here's the main part we're going to do. Boolean has access, given a string folder. I'm going to do a little bit of input validation just to make sure. Strings dot is empty, or something like strings dot is null, maybe.
Right. Is this within the graph class?
Yes.
Oh, okay.
All of
Let
this
me
is supposed
bump
to be in
down this semicolon.
Yeah.
Or
no
this
worries.
bracket.
It's just like in our
Okay.
class.
Yeah. Cool.
This API I'm not so sure about, but it's fine. Let's
Okay.
just assume there was.
We can
is no
adjust
thing.
the APIs you go in. So
Yeah.
as the needs present themselves.
No worries. Okay, so just in terms of like the validation, could you ever ask for a folder that was empty?
Could we ask for a folder that was empty? What do you mean empty?
Like the identifier itself was empty. Like, do I have to do any kind of validation? Like,
no.
like it's like empty
don't,
strings.
No validation where
All right.
identifier would be empty.
Okay, cool. So I can just drop
But
that.
you can leave that. But yeah.
Okay, sure. You wanna? If
For me to leave, it doesn't matter.
it was always be false because it doesn't exist.
Okay.
Now let's basically do like a depth first traversal, and then we can do it like iterative or recursive. Is there a preference? I can do it either way.
No preference, whichever you're more comfortable with.
Okay. Let's see if I can flex my recursion muscles. Okay, as long as you're traversing. Okay, now that I'm thinking about it, I will have to come up with some kind of constructor here, folders and access.
Right.
Okay, just so I can make sure that like at any given point, do I know whether a node has, whether a user would have access to the node or not?
Yeah.
Okay, so by the time the graph is constructed, I know for a fact that every node knows whether the user has access to it or not.
Yeah.
Okay, so now let's start at a, let's do the iterative approach to begin with. I think that's the one I have to change the least code in. Okay, so let's think about it. So we start somewhere in the node. So like the root, let's say, right? Private final node is going to be the root. So the root starts somewhere. It's fine. We'll set it here. Set some node. That's fine.
Okay. Yeah, it can be like a dummy node or just empty or.
Exactly. Yeah. So let's start at the root is not equal to null. So let's traverse down. So let's start. We'll need a stack and stuff. Let's just replace it with like. Let's just replace it with a recursive version. Okay. So if let's do the base cases. If node equals null and you haven't returned true yet, you'll return false.
Right.
Okay. What is the other one? So if it's going to be called root.
Right.
Okay. So let's say if root dot has access is true, then you return true. Okay. That's not true. If the folder you're looking for is equal to the root and the root has access, if you're already at the node you're looking for and it already has access, you can return true.
Mm-hmm.
That's another valid statement.
Mm-hmm.
Okay. So now what's the other case? You're at a node that is not that doesn't have access,
Right.
but your parent did.
I just want to bring something up.
Sure.
So we have this top level variable root in the class.
Yeah.
One thing I worry about is shadowing. I don't know if this is an issue. So we have the root variable at the top level.
Yeah, you're right. That's a good point.
Yeah, just so we're not like caught in like a crazy debugging thing.
Yeah,
later.
absolutely. Yeah.
Maybe
That
it doesn't
totally
cause an
makes
issue semantically.
I can replace with like current node.
Sure.
That's totally fine. Yeah. And I'll just pass down root in the beginning. Okay, so how do you pass information down to your children in this? You can still pass it down as a Boolean, I suppose, right? You can just say like access tree children have access, let's say. So essentially this is the idea I was talking about where you propagate the data down.
Right.
If you identify that you yourself, not root, I was just calling it current node. If you have somehow identified that current node has access, you can essentially start passing this information down to your children.
Right.
Actually, you don't even need to do this. You could just do return has access current node dot left. Actually, one of the things I should have clarified is can a folder, it should have multiple children. Even though the examples make it seem like you can only have two child, right. I think it's best to assume that you can have multiple children. Mm-hmm. Right. Okay, so the node class should actually have multiple children.
Right. Yeah. A node will have, okay, the access Boolean of whether we can access it, the identifier, as well as, what are below it. If we go fully through with how we're modeling this. And
Yeah. Is that a fair assumption that you could have like multiple children?
yes.
Or it's just going to go with
you could
this?
have multiple children or no children.
Okay, cool. Let's not make it final. Because children can be dynamically constructed, we can do like public void add string child, and then just continue adding to the list.
Right. So we're looking at the hasAccess call. I believe we have to construct this. At some point, we'll have to get to the construction of the graph.
We will, yeah.
Yeah. Okay.
Get children. I just want to, just in the interest of time, in an interview, I would get to the main logic first.
Sure.
And then try to go back.
Yes, I agree.
Okay, so this would just be some getters. Okay, so here what I would do is, because I can assume that like there may be more children, current node. So for each one of them, I basically have to call, child node, the folder I'm searching for, and then current node dot has access. So essentially pass down. So let's think about this. If I was at any given node, and I'll run through an example test case after.
Right.
Okay, so we have identified that if you're, let's say this was like the top.
Right.
If you find yourself have access and you're also looking for yourself, then it's a true case.
Mm-hmm.
Okay, if not, for each one of your children, you'll recursively call this function that we've defined, and you'll pass it down whether your level of access is valid. So if you had access, you would pass that information down to your children, and your children here would check, no, children have access. Okay, so here
so
the
this is
base case
interesting.
will
You're
be-
returning in the for loop. If that, you see what I'm...
Oh, yeah.
So I would imagine we want to do some sort of aggregation across, did we detect some...
So, true, because you don't want to find that's a good point. You don't want to find the first child that failed. So you could like, you just want to aggregate across your Booleans, right? And just return like an OR of them, essentially. Let's think, what's the best way to do this? Okay. All right, so yeah, we talked about like maybe marking the access while we're like constructing the graph. Actually, I keep skipping the graph construction. Maybe I should start there so that we can decide like when to mark these nodes with access.
Right.
Because now I'm thinking I'm going down too much of a complicated route. There may be a
we can
easier
look
way to
back
do
at
this.
the
let's
input
look back at the input
and think about how we would construct this structure.
Yeah, actually, I should have taken a deeper look here. So, how are we given the input? Actually, is it naturally like you go from a node to its child?
Yes. So on the left, we're going to have, if we look at this folders 2 example up here, we're going to have the node itself, and then it points up to its parent. So
it points up to its parent.
Yes. So node to parents.
Okay. Yeah, I guess me saying left parent, right child. Oh, so this was wrong. It should be left child essentially in this format. Right is parent.
Correct.
Oh no.
Pointing up
Okay.
to parent, yeah. And so
that's fine. Yeah.
Okay.
I don't think it's so. If you're pointing up to your parent, actually that kind of makes it easier, because if you're being asked for like a particular node and you have access to your parent in the initial list, you could always just traverse up instead of traversing down.
Yes, and we did look top down, bottom up. We saw both ways. You gave us a conceptual overview. Either work to implement. So it's whatever you would decide.
It's actually a funny thing is it's actually harder to build a graph given this data input.
Right.
Because I thought it was parent to child.
Right.
But if you're already given your parent, you essentially actually don't even need a graph. You can just have like a map of your parent. So like let's imagine you could just go to your parent and your parent can go to its parents. At some point you reach the top of the tree. Yeah. And if at any point in this backwards traversal, essentially the topwards traversal, but now you just move backwards. If you find a parent that has access, you're good. Yeah. Okay, so that's a small mistake I made. I should have clarified whether left right was parent. Okay. Given this data structure, I'm saying. And this may be controversial, but I think we can just give up on this approach and just move back to like moving bottom up. Sure. Because I think the data naturally leads itself better to a bottom up.
Bottom up also works. You could implement that if you'd like. Yeah.
So just for it to be educational, I think the top down approach would have lend itself well to like multiple queries later on.
Right.
Like if we had built up a system like that, where essentially it would be a database and you could query it at any time. But just based on how like the graph is given to us, we basically don't even need a graph at this point. We can just have like a hash map.
Right.
Okay. So
and what advantages does, what makes you think we need a hash map here, or a hash table, hashing structure, dictionary?
Essentially for like constant time lookup, if you translate these, if you translate this list into like a where you can just point to its parent, really you want to keep traversing upwards, right? So I suppose this could be like a reverse graph, but even a hash map works because as long as you can get to your parent A, at some point you have to query your parent's parent.
Right.
So if this was now a key to its parents in the map, you could do a constant time lookup.
Right.
And always get to your parent. So this just allows you to like traverse up the tree in a just an easier manner and quick access.
Right.
So that would be my reason for using like a hash map. And maybe it doesn't work. But I think largely what I'm going for is like if B can point to A, and then at some point A's parent is X, and then at some point that X's parents are whatever, G and H. Now you traverse down to G and H, and you try to find their parents. So now you can go parent up, and then you can find like M, and then you can find like H.
Yeah. I think, conceptually, I think we have a good overview. I think, you can proceed to implement this.
Cool. So I think step 2 would just be traverse up, and find access point. That's fine. Okay, so let's just go through this then.
Okay.
Folders. You can iterate through, and then you can just create let's do a map for now. And we did mention that a single folder can have multiple parents, right?
Right.
So folder tree, let's call it tree.
Well, a folder can only have a single parent. Since this is a tree, a folder can have multiple children, but only a single parent.
In this example, oh, true. Technically, you only have one parent.
Yeah.
You just had like a recursive parent up.
Yeah. So essentially, the folders we're receiving are going to point up to the parent, and we're starting from a lower node. And you describe the bottom up approach as climbing up the tree. Mm-hmm. So we're only dealing with child to parents as a 1-to-1
True
mapping.
That's a good point. True. You don't really even need to consider multiple parents. You just find your parent, and your parent has a parent.
Yes.
So this could essentially be a hash map of string to string, where you're only pointing to your own parent.
Correct. Yes.
Okay, so I'm just going to use the map interface and then keep a hash map implementation.
Right.
Always a good idea to do that. Okay, and then you can do like a folder tree. This folder. Oh no, it's a list of array of folders, where the first is always, and there's always 2 entries in this list.
Yes, it'll always be well formed with the index 0 and 1.
Folder 1. So just to re-specify the structure, because I got this wrong first time, is the map will be from node to its parent.
Correct. At all times. Yes.
So the left side, the 0th index is always the current node, and the right side is always its parent.
Correct.
Okay, cool. So now at the end of it, what we should really have is a hash map that's just has references to its parents. And now what we can do is, so this was step 1, we could decompose into a hash map.
Right.
And now if we have to traverse up, we can start at the folder that we were given, right? And then essentially this can be a while loop where we say starting point is equal to folder, starting point is not equal to null, because at some point something won't have a...
Yeah. And is the starting point the kind of current pointer we're going to hold as we're like climbing, or...
We may not even need this actually. We can just start at the folder and just keep doing gets.
Okay.
You might be right. We can just start out at...
Or more so, I was just saying we might want to rename the variable from starting point to maybe like current, or something where it's like we are starting at the folder we're querying, but we are climbing up the tree, so it won't always be the starting node. More so, it's just a naming thing I was mentioning.
Oh, okay. Yeah, totally. Start with like current, and then... Yeah, we can just change what this points to. So while current is not equal to null, you can keep setting current to be its... Well, the first thing you want to check is like if current, if the access list essentially,
right,
dot contains Does set have a dot contains or is it a has?
I think it's been a while though.
It's been a while for me too.
Right.
You should use the language you're most comfortable with. Don't make the mistake I'm making.
Right.
But we can do this. So if you found a access list that has at any point, then you can just return true. It might be contains actually. I don't remember. But okay. So if you can find, let's think about it. If you can find yourself in the access list, you're fine.
Right.
You just have to set yourself to be folder tree dot get current.
Right.
And now you point to your parent.
Now it's popping up to the parent, and then next
you love
iteration.
to the parent. Yeah. You keep checking. If at the end of all this you haven't returned true yet, you'll return false.
Right.
Because you were never able to find yourself. And then at some point, folder tree dot get current will be null. Let's think about that. Okay. And I think this is okay, but I'm just going to run through a quick test.
Right.
Just to make sure.
Sure.
So let's walk through the initial example of ABC, just to be simple. And then you were targeting folder A, and the access set was empty in this example.
Mm-hmm.
So let's just move this down. Example 1. Okay, so let's imagine we go down here. We construct the folder tree. We get A and B.
Yeah.
It becomes this. A points to B. Or no, sorry, I make this mistake again. A points to nothing.
Mm-hmm. Yes, A
points to null. Yeah. And then B points to A, and then C points to A, correct?
Right. And also feel free to run the code. Like if you
I can actually run? Oh, that's fantastic.
Yeah, feel free to run it at any time. To me, this seems like it will probably work.
Sure. Let's actually run the test. So this is in the main class. We can run public void main, check folder access. I think I've implemented that, right?
Check folder access. Yes, that is the name of the function.
But I did not call it that, did I? Oh, I did.
No, it's
I did.
properly.
Oh, fantastic. Okay.
And hopefully this runs. I think this should.
Let's try it really quick. In an interview setting, I would recommend you look over your code first. String folder. What am I doing wrong here? Is already defined in the method check folder access. That's okay. I'll just call it like current folder. The folder is just the target folder, I suppose. Right. Okay, that should be okay.
Okay, false. Let's see. Okay, yeah, false, true. Looks like that worked. So let's imagine we remove this B from the access list, and we try to access G. We should see false on this run. Access to I just
cannot be applied to given types.
Oh,
you just removed it.
Yeah, I just did an empty add. So let's see if this works. Everything looked correct to me. False. Okay, cool. Yeah. So this approach looks correct to me. So I think we can pause with the debugging. This looks reasonable to me. Let's think about what is the efficiency of this, and what is the efficiency of? Let's imagine we did go with like a top-down approach. Could you like compare them? The top-down, bottom-up, the efficiency, the advantages of each, time and space-wise.
Cool. Yeah. So just for a runtime thing, we can look at like all the loops that are essentially running.
Right.
The folder tree map is going to be essentially constant space. Well, no, it depends on how many inputs there are. But from the runtime perspective, you are iterating through the list of folders once.
Right.
So if the folders were of size n, you're iterating through it n times here. And then here at worst case, let's say you have to traverse all the way up to your first parent. You're just traversing this map of size n.
Right.
The keys in the map. So this part, at worst case, you're accessing. You're accessing every key in the map. And how many keys could you have in the map is equal to, let's say they were all individual isolated folders. Technically, that's the worst case.
Right.
No, that's not the worst case because then you would hit null first. What's the worst case here? The worst case is that you have like one child. Everything has one child minimum.
Perfect. Yeah.
And then they are all pointing to each other.
Yeah. We don't always imagine this is like a balanced kind of tree.
Exactly.
This could be something where, it's a parent, and it's just like a linked list all the way up.
Yeah, exactly. That's what I was thinking.
So, yeah.
So
what would that be in terms of like time? What would that like down to?
So here you end up mapping through O of n,
Okay.
and here in the worst case you end up mapping through O of n.
Okay. And let's imagine it's balanced. What would the bound be? Let's imagine it's a perfectly balanced folder tree.
Balanced folder tree.
Yeah.
What do you mean by that one?
Let's imagine that. That the tree is perfectly distributed, so that it's like a perfect binary tree.
Okay.
Like, what would the time complexity be if it was a binary tree, perfectly balanced?
Perfectly balanced binary tree. So every
At worst.
every node has just one parent.
Yes.
And then what would that end up looking like?
It would be better than linear.
It would be better than linear.
Yeah.
You're right. I suppose what would that look like? Having two folders be with one parent, right? That's what you're saying,
Right.
like A would have like B and C,
Yeah.
right? So the map ends up looking B
A
points to
would
A.
have, or more so, I'm just saying, like, if we had a binary tree of the
Sure.
folders and it was like perfectly balanced, what is the worst case climb distance relative to the total amount of nodes?
I see what you're saying. So
Yeah.
if you had like n nodes, like it'd be
Yeah.
like log of n, right? Because you're
Yeah.
traversing up
Yeah.
the tree, and the worst case is you go up like the
Exactly.
height of the tree.
Exactly. Yeah.
So-
Which is logarithmic. design.
Yes.
Yeah.
So it would be O of log n.
Yeah.
Log n in the
Perfect.
best case case where you just traverse the
Right.
height of the tree.
Right. So I think that's good for time. In terms of space,
Yes.
what would that look like?
Yeah. So space you have to represent the map essentially. That's because everything else is just a constant value.
Right.
Just one variable here, just one
Yeah.
variable here. So the only data structure you're maintaining is this map,
Right.
which is just mapping in the worst case, it's mapping. If we were saying you can only have one parent, it's just how many ever nodes there are, right?
Yeah.
So
linear
it'll
bound.
just
Linear
be-
bound. Yeah.
it'll just be
for
linear
the
time.
amount of folders.
Sure. So ultimately, it ends up being just how many ever entries you have passed in. So
Exactly.
and in the best case, that's still the same thing. So
Yeah.
space-wise, I don't think you can do any better. Time-wise, yes, if it was well-formed, you could get better into log of n.
Yeah, no, I think that's perfect for the time and space. That's exactly what I was looking for. So, okay, I think we're good on the time and space. And I think you did great with the problem. You broke down like the different angles we could look at, the trade-offs, and so on. All right, we can step out of kind of the problem-solving mode, and let's talk about like how you think that went, and kind of, how has this compared to other interviews you've done, and just like how do you feel about overarchingly how things went, so the flow of things.
Yeah, for sure. I think one of the things obviously I got distracted by was my concept of going top down. Right. And obviously I talked about the top down approach where you could get a lot of benefits from like, if you essentially form a database that you query against at all times and you can get the answer really fast.
Yeah.
So if it was like a persistent system where you can hold on to this graph forever, then you can do like consistent queries. And as the set builds, you can like repass it through a couple of times and then you can do that. So that's like the ideal case scenario. And I got stuck on the top-down approach because initially I actually made the mistake of thinking the data given to me was in a graph format. So I think one of the things I could have done better, and this is something I would recommend everyone do, is reassess your assumptions at all stages and just look through the input again.
Right.
And it's good to skip the step where I said like, I'll construct the graph later. Yeah. If you know for sure that's what's going on. But what I should have done is looked at the input again, seen if a better data structure would have worked. In terms of other things,
and for me, it's like as the person orchestrating this, I could have not let us down that way, but I think it's a fine way to go.
It is, yeah.
It's a bit more code than we need to like solve exactly what's at hand, but it's a completely valid way. And I still want to see that trade-off of like, what if we did do it that way? Because it is a valid way to, what if we do build a persistent file system and then like cache data at every node, and then we can do incremental updates, and then we have constant time checks against that system. So that's a fine way to do it. But just like given the way we have the problem, doing the climb up solution, which is the one we ended up doing, I think is like the most succinct.
Ultimately, I think you have to like solve the problem that's given in front of you. As an interviewer, what I try to do is when a candidate does exceptionally well on a problem, I try to expand the problem such that their previous solution, if they have written it well, they can expand on it. I think I got too stuck in that mindset. So it is a trade-off decision to make, as like you may anticipate an extension to the problem, so you don't want to get too tied down into like a very specific implementation, but ultimately you should solve the problem before you here the bottom up approach works totally fine, but if there was an extension part, I would probably go down to the top down approach.
Right. And then what are other kind of Are there any other tips you would give in terms of like interviewing, like your number one kind of thing you'd want to pass on to people that might help them in their interviews and so on?
Yeah, for sure. I think here, obviously being in a recording interview setting,
Right.
it like adds like extra pressure to perform differently.
Right.
And that pressure is different in a interview where you think like, oh, I won't get this job. You
Right.
like start panicking and everything.
Right.
I think 100% one of the main things you can do is like, it's okay to actually get the wrong answer. I've been in other sides of interviews where the candidate does the wrong answer,
Right.
but they are thinking about it so deeply and they're like so involved in it that even if they are in the wrong path, I think the fact that they can talk intelligently about the problem often signals like a lot of good things. So even if you feel like you're totally struggling, just start talking about like trade-offs, about like what you may be doing wrong,
Right.
write down your assumptions. I think one of the main things I like to do is put comments at every step where you can at least describe what you were doing before you do it. Like plan out what code you're going to write. So here, for example, like when I said like step 1, decompose into a hash map. If this assumption is already wrong, your interviewer will point you in the right direction.
Right.
So start with comments, write code essentially last once you've like agreed on a solution. Don't panic. Obviously, that's like easier said than done though. I totally understand.
Don't panic. I'm panicking.
Do well. Yeah, of
Right.
course.
Right.
It's a pretty generic tip, but I do think it works ultimately. Like, sure, if you don't pass this interview, there'll be another one. I'm not actually that good at programming interviews. I failed many more than I can count.
I think everyone, even the best, like
Even
I
the
think
best, yeah.
the distribution of like fairness / outcomes, I think even for the, well, I don't know about even for the best, because some people do pass a
some
lot,
people
but
are, like,
you know,
nuts.
some people are brilliant engineers and just fail a lot.
Indeed.
So
That's
I don't
true.
know. It's not the most consistent thing. But anyway, yeah.
I don't claim myself to be like a brilliant engineer or
Right,
anything, but it's just like a lot of these problems you actually don't see in a job too. So
Yes.
it is a way for an interviewer to check like how sociable you are, how well
Right.
you can work together with them.
Right.
So if you look at it as much as a pair programming exercise as you can, I think that's the best you can do.
So I want to thank Sam for his time. If you want to practice this problem, you can practice it on interviewpen.com. We publish 2 to 4 videos a week on data structures and algorithms, as well as system design topics. So if you want to get more practice with something like this, you can visit our site. We have plenty more instructional lessons. So I want to thank Sam for his time, and thank you for watching. Okay, that's it.
Fantastic.